Right, so our second section for this week is 8.3, which is on complex numbers. Okay, specifically writing complex numbers in what we call trig form. Right. We're used to working with complex numbers in standard form. Okay, this is the standard form of a complex number. Okay, standard form is a plus bi. So you have a real part plus or minus an imaginary part. Okay, so an example of a complex number is 2 plus 3i. Let's say 7 minus 4i. Even just a number like 6i. That one doesn't have a real part, so in this case the real part is what?
6.
Well, the imaginary part is 6. 0. Okay, you could think of it as 0 plus 6i. Right? There's no real part there. Okay, the other examples I gave had both a real part and an imaginary part. Okay, even this is a complex number. What's the imaginary part of 8? 0. Okay, 0i. Right, so working with numbers in standard form is fine, especially adding and subtracting. That's pretty straightforward. Okay, we learned that if you're going to add and subtract complex numbers, you basically combine the real parts and combine the imaginary parts. So if I was going to add these up, I would add the 2 and the 7 and get 9. And I would add the 3 and the negative 4 and get negative I. So 9 minus I is what you'd get if you add these up. Right, so adding and subtracting, we already have a pretty easy way to do it. It's multiplying and dividing. In standard form, that's kind of a pain. Right? That takes a long time. And even worse is when you want to take a complex number and raise it to a power, or reverse that by taking a root. Okay? Raising this to a power and taking roots, very difficult. Doing it in trig form, it's a lot easier. Right? So today we'll look at multiplying and dividing. Tomorrow we'll look at raising to powers and taking roots. Right, so before we get to writing things in trig form, one thing we have to know is how to graph a complex number. Right, so when you're graphing a complex number, like a plus bi, it's basically like graphing the point a comma b. That's all that it really is. So instead of having an x-axis and a y-axis, okay, which is what we're used to having, when you're graphing a complex number, you have to graph the real part, and you have to graph the imaginary part. So we graph the real part on the horizontal. Okay, we call that the real axis. And we're going to graph the imaginary part on the vertical. Okay, that's going to be the imaginary axis. And the directions are exactly the same as what you're used to. Positive is up, negative is down. On the real axis, positive is to the right, negative is to the left. Okay, so what we'll do is just practice me giving you some complex numbers, and we'll graph them. Okay, does everybody have that diagram? Real and imaginary axis? All right, so let's graph these points. Right, let's just label it, make sure we remember. My horizontal axis is which one?
Real axis.
That's my real. And the vertical is my imaginary. Okay, so I want to graph the point negative 4 minus 2i. Right, let's just start by identifying what the real part of this number is and what the imaginary part is. And when you answer both of those questions, your answer is just a number. No letter attached. Okay, just tell me a number. Okay, Nick, what's the real part of negative 4 minus 2i?
Negative 4.
Yep, real part is negative 4. Brian, what's the imaginary part? Negative 2. All right, so we have to go negative 4 on the real axis, negative 2 on the imaginary, and then just put a dot. Right, so Jamie, how do I go negative 4 on the real axis? Yep, we're going to go left 4. And Amanda, how would I go negative 2 on the imaginary?
You'd go down to.
Down 2. That's it. That's the point, -4 minus 2I. All right, let's try graphing -2 plus 3I. Brendan, how would I graph -2 plus 3I? Starting from the origin.
Left 2 up 3.
Yep, left 2, up 3. It's -2 plus 3I. Oops. Do it. All right, how about 5I? Okay, well, first, what's the real part there? 0. Okay, so we're not moving left and right. Where am I moving for 5I? Up 5. Okay, so that's 5I. And the last one is 6. We're just going right 6. The imaginary part, think of it as plus 0I. Okay, any question on graphing complex numbers in the complex plane?
Will this be on testing?
You're going to have to know specifically what quadrant a point is in to do something. So that's why I showed you how to graph. So, for example, if I wanted to change this point, -2 plus 3I, into trig form, the first thing I have to know is what quadrant it's in. Okay, and that will be on the test, changing it to trig form. Okay? Okay, any questions on that? Okay, just a reminder about your quadrants. Okay, that's 1, 2, 3, and 4. All right, so when we want to find absolute value of a number, when you learn about it way back when you just study basic absolute value, not with complex numbers, we usually define it geometrically as the distance from what? What's the absolute value of a number? It's the distance from 0. Okay, that's a geometric way to think of it. You're thinking of it as a picture, how far away it is from a point. Okay, well, we're going to now find the absolute value of a complex number. But in the complex plane, we don't really call it 0 because it's two-dimensional. What do we call the point that would correspond to 0? It has a name, it's a word, where 0 is.
Origin.
The origin. Okay? So usually when you have a two-dimensional coordinate system, the point is 0, 0, you call it the origin. And to find the absolute value of a complex number, that's all you have to do, is find the distance from the origin. All right, so I'm going to go back, and I want to take a look at the points we just graphed. And let's just pick this one in quadrant 3. Okay, -4 minus 2I. What shape could I make out of that would help me to find that length? Yeah, I can make a triangle out of it just by going like this. And now, what in that triangle do I really want to find that'll tell me the absolute value of this point? The hypotenuse. Okay, I already know each leg. That side is 4. That side is 2. Just use, well, what theorem do we use? Yeah, just use the Pythagorean Theorem to find the length of the hypotenuse, and that's the absolute value. Okay, that's the distance from the origin. All right, so if you're using the Pythagorean Theorem, it would be a squared plus b squared, and then equals the hypotenuse squared. But we don't want the hypotenuse squared, we want the hypotenuse. So you add them, you square each one, add them up, and then take the square root. And of course, since absolute value is a distance, what kind of number would you never have for distance? Negative. You could have 0, but you would never have a negative.
If you have 0, does this mean that it's not a triangle?
Right, if the distance from the origin was 0, you wouldn't be able to really draw a triangle, because where would your point be? It would be right at the origin. Okay. So if your point is right at the origin, then the absolute value of it is 0. Okay. So any questions on the idea of what the absolute value of a complex number is? Okay, and this we're going to do in standard form. Okay, trig form doesn't really provide us a fast way of finding absolute value. In fact, absolute value is easier to do it with the kind of points that we're comfortable with. After this one, then we'll start to get into trig form. All right, so 3 plus 4i. If you want, you can make a sketch and you can draw the triangle, or just use the formula. Square the real part, square the imaginary part, add them up, and take the square root. Okay, when you square things, this is A, this is B. The I is not part of anything that you square. Okay, you're only plugging in numbers. So can anybody tell me what my equation would be? And then we'll simplify it. Eric?
3 squared plus 4 squared.
Yep, 3 squared plus 4 squared, take the square root. That's going to be 9 plus 16, which gives me the square root of 25, or 5. Right, so in that case, we got a nice answer because I picked 2 numbers for the legs that worked out nice. It's a 3, 4, 5 right triangle. If you ended up with an answer that was a square root, you do need to reduce it. Okay, if it comes out to 1, you can reduce. For example, if you had, let's say you did all the work out and you got square root of 20. Okay, this is not a good final answer. What would the square root of 20 reduce to? 2 square roots of 5. Yep. Okay, to make sure you follow all your rules with square roots, reduce anything that you can reduce. Okay. Any question on finding absolute value? All right, so now we're going to look at trig form. Okay, so for the rest of today and all of tomorrow, what we do with complex numbers is going to focus on trig form. All right, so this is the standard form, okay, of writing a complex number. I used A and B for my letters before. Okay. I'm using X and Y now because we're going to think about it graphically. And X and Y are the letters most people use when they think of graphing. Also, you might have noticed I put the I in front of the Y. We had the I after it when we wrote A plus BI. If you want to put the I after, that's fine. It's just the final formula I'm going to come up with. They put the I in front, so I'm following the way your book does it. All right. So what I've done here is graph this point xy. Okay, again, pretend it's a complex point. I'm doing it in quadrant 1 to keep it simple. And the 2 legs of the triangle are x and y. Okay, and I've labeled 2 other things I want to find. Labeled something r, and then the angle between the hypotenuse and the positive x-axis, I've labeled theta. Okay, and I want to find these 2 things. Okay, and the way we're going to find it is to use right triangle trig. Okay, so I put my point here, drew in a distance to the origin. It's almost like I'm drawing in my absolute value. And then I drew a line straight down to the positive x-axis. Okay, same kind of diagram as when we do absolute value. Let's start by taking the cosine of theta. Okay, how do you do cosine? Cosine is what side, just in general, like, is it opposite, adjacent, hypotenuse, what is it? Yeah.
Opposite over hypotenuse? Adjacent.
We're going to use opposite over hypotenuse for sine.
Oh, I was thinking the wrong thing. It's adjacent over hypotenuse.
Adjacent over hypotenuse. Okay. In this triangle I just drew, what side is adjacent to theta? Yep. X. And what's the hypotenuse? R. Okay. My goal is I want to get x by itself. So when I'm done, I want a formula for x. Okay. How would I get x by itself in this equation? Multiply each side by r. So r cosine theta. Okay, so x is r cosine theta. Now I want to do the same thing for sine. Okay, I'm going to get a formula for y in a second. Okay, what's the sine of theta? Okay, opposite over hypotenuse. And Cameron, what side is opposite theta?
Y.
And the hypotenuse again?
R.
R. And I'm going to multiply each side by r again. So r sine theta equals y. Okay, if you've done any work with vectors, has anybody done work with vectors? In physics, you've probably seen formulas similar to this, breaking a vector into its horizontal and vertical components. That's kind of what we're doing here. Okay? And our next unit that we're going to start on Thursday is vectors. Right, so this kind of leads into it a little bit. All right, so now what we're going to do is take our formula for x. We're going to take our formula for y. And we're going to fill them in those two spots. And what that's going to do is it's going to get rid of the x and the y. And instead of an x and a y, now we're going to have a radius. Okay, that's what r stands for. Think of it as a radius. And we're going to have an angle. So our two letters are going to go from x and y to now having r's and thetas. Right, so just substitute in what's in those boxes in those spots. So for x, we've got r cosine theta plus, okay, the I stays right where it is, and then y is r sine theta. Okay, now, besides the argument to each trig function, what else do they have in common? They have an r. Okay, and what can you do when you have two terms and they have the same thing in common? You can factor it out. Okay, so what I've done is it's the reverse of the distributive property. I factored out an r. And I end up with r cosine theta plus I sine theta. This is the trig form of a complex number. Okay, so it's based on two things. You have to know how far your complex number is from the origin, and you have to know the angle it makes with the positive x-axis. Okay, so that's what I just said. Okay, you need r, and you need theta. Okay, if anybody's done any work in their shop with what's called polar coordinates, or you've ever used polar, what we're doing right now is basically polar coordinates. Okay, so you might hear me say, write it in polar form, or you might hear me say, write it in trig form. If I say either one of those things, they mean the same thing.
Can you scroll up for just a second? I missed like one little piece of it. Where did the I come from?
Where did the I come from? The I, that's part of the standard form of a complex number, x plus iy. So we just carry that I down.
Oh, okay.
Everything else we substituted in for. Okay. Right, so when you write a complex number in trig form, that's a final answer. Okay, so let me show you how a final answer would look. Let's say you had a radius of 2 and an angle of 45. Okay? If you found that that was your radius and that was your angle, this would be your final answer. 2 cosine 45 plus I sine 45. That's it. You don't do anything else with that. Okay? That's an example of a final answer. Right? So there's two things we have to find, r and theta. Right? So now we're gonna draw a diagram and see how do we figure out those two things. Okay. Again, this is just an example I made up. We didn't calculate anything. I just made up r and I just made up theta. Right. How do we find r and theta? Right. So there's our point. Does anybody have a guess how we're going to find r? What do you think I want to maybe draw first here? Yeah, we're going to make a triangle. That's r. It's the distance from your point to the origin. Okay, and to make a triangle, you always draw your leg perpendicular to the x-axis. Don't draw it to the y-axis. All right, so the hypotenuse is r. How long is the bottom side? Well, we don't know a number, but keep in mind we know the location of this point. So the bottom side would have to be x, because you went to the right x, and the height? Y. So based on that, how would you get r? Yeah, the Pythagorean Theorem. It's just like finding the absolute value of a complex number. Okay? So r squared equals x squared plus y squared. Okay? And we need to find theta. What trig function would we use to find theta? Keep in mind, we're going to know x and we're going to know y. You don't want to use r to find theta because r is something you're going to calculate. Tangent. And I heard somebody say it. What is tangent?
Or opposite over adjacent.
It's opposite over adjacent. And now, I don't want to know the tangent of theta. I want to know theta. So we take the inverse tangent of y over x. All right? Yep. Okay, so to find r, you're going to use the Pythagorean Theorem. R squared equals x squared plus y squared. And to find theta, you use the inverse tangent of y over x. But that formula will only work in quadrants 1 and 4. Okay, we talked about way back when we started inverse trig, we said that inverse tangent is always between two numbers, negative this number and positive this number. Does anybody remember what inverse tangent is always between? It's negative this number to positive this number. Yeah? Not, so you're thinking like if you graph sine, the highest value is 1 and the lowest is -1. We're thinking in terms of an angle. It's negative this angle to positive this angle. Yep? No, not negative 180 to 180. If it was negative 180 to 180, it would cover the whole thing. It's negative 90 to 90. Okay? Anytime you use your calculator to do inverse tangent, it's always going to give you an answer between negative 90 to 90, which is from here to here. It'll never give you an answer in quadrants 2 or 3. And that's a problem, because we could have answers in quadrant 2 or 3. So what would you have to add, do you think, to get to the other half of this circle? Yeah, if you add pi, or 180, what that'll do is give you an answer in quadrants 2 or 3. Okay, so if you're in quadrants 1 or 4, you're going to use inverse tangent y over x. If you're in 2 or 3, you're going to do 180 plus inverse tangent y over x. Well, how do you know what quadrant you're in? That's why I showed you guys how to graph complex points. So you graph it and then figure out your quadrant. Now, is there any other case you could have besides being in a quadrant? You could be on an axis. And let's look at what happens if, for the coordinate, say, on any coordinate on the positive x-axis. If I wanted to write the coordinates of that point, what's the x value if I'm on the y-axis? The x value is 0. I don't know the y value. It could be 0.3, 0.7, 0.10, 0 something. What would happen if you tried to plug in an x value of 0 into inverse tangent? It'd be undefined, right? You're dividing by 0. Okay? So these formulas don't work when you're on an axis. Okay? When you're on an axis, you just have to know you have 4 choices. If you're on the positive x-axis, it's 0. If you're on the positive y-axis, it's 90. If you're on the negative x-axis, it's 180. And if you're on the negative y-axis, it's 270. Okay, you just have to memorize 0, 90, 180, and 270.
Can you put that in for x?
That would be your angle. That's how you would find theta.
Oh. There's no math, dude. There's no math.
Nope, there's no math. So for example, if I said to you, here's the point 0 plus 3i, and I said to write it in trig form, you don't even really need Pythagorean theorem when you have a 0. Graph the point 3i. What's the radius? What's the distance from the origin to that point I just drew? 3. You don't really need to say 0 squared plus 3 squared equals r squared. Okay? If you're on an axis, all you have to do is count how many units you moved. Okay? When you're not on an axis, then it's like you're finding the hypotenuse of a triangle. And what would be the angle for 3i? It's 90 degrees. It's at the top. So you just have to memorize the top is 90. Okay? So this would be a very easy point to change to trig form. R would be 3, theta would be 90. And you'd fill those two things in these two spots, 3 and 90. And that would be it. Okay, but we're gonna go through a few where you actually have to do out some calculations. All right, so let's find the trig form of negative 2 plus 2i. Okay, what letter is this negative 2? It represents x, and the positive 2? Y. So they're starting us off with an x and y. What 2 letters do I need to find to put this in trig form? I need r, and I need theta. So this is my goal. Find these 2 letters, and then write the answer. Okay, let's graph it. Okay, so to graph it, I'm going to go left 2, up 2. Left 2, up 2. Now, this problem didn't say you have to graph it, so my sketch is just to help me. I'm not grading the sketch. It's just to figure out which quadrant I'm in, and maybe if I want to draw a triangle, I can use it to do that too. But all I care about is that you get r and theta correct. Okay, how long is each leg in this triangle? They're each 2 units. Okay, let's do our Pythagorean theorem. 2 squared plus 2 squared equals r squared. What's 2 squared plus 2 squared? 8. And after I reduce it and simplify it, what's the square root of 8? 2 square roots of 2. That's my radius. Okay, any question on the radius? All right. Now I have to find theta. Theta is this angle right there. Now, sometimes you can kind of reason out without going through the formula. For example, in this one, you could kind of think it through logically. What kind of triangle do I have? This is a special triangle. It's a 45, 45, 90, okay, because it's isosceles and it's a right triangle. So if you know that this angle is a 45, and you know all the way around is 180, how much is this big angle? Brendan?
135.
It's 135. Okay, but let's say you couldn't use that kind of reasoning to figure it out. Let's go through the formula and see what we get. Okay, Derek, what quadrant am I in? 1, 2, 3, or 4? We're in quadrant 2. What's my formula for theta in quadrant 2?
10 negative 1 y over x plus pi.
Yep, so we're going to go, I'll do this one in degrees. If you want to do it in pi for radians, that's fine. And what do you call that last thing you said?
Inverse tan.
Good. Inverse tangent. Y over x. 2 over negative 2. Okay, you shouldn't be plugging the I in. Okay, you're plugging in x and y. All right, so we get 180 plus, what's 2 divided by negative 2? Negative 1. So you're really taking the inverse tangent of negative 1. If you do that, you will get negative 45. And then what's 180 take away 45? There's where your 135 comes from. All right, so now we've got the 2 things we need to write our final answer. Now we actually have to write it. So final answer is r, parentheses, cosine theta, plus I sine theta. Okay, people have asked me, well, what do you do? Do you do anything with that? No, you just, that's it. You leave it just like that. Okay, if you were to take this 2 root 2 and distribute it out to cosine 135, and then distribute it out to sine 135, what you'd be doing is reversing everything we just did and changing it back to what we started with. Okay, so if you want to check your answer, you can try that on your calculator. Take 2 root 2 times the cosine of 135, and I guarantee you'll get negative 2. Take 2 root 2 times the sine of 135, and you'll get a positive 2. And don't forget that part has an I with it as well, so 2I. All right, so we don't want to change it back in this problem. At some point, maybe I'll do one out just to show you that it works, but not right now. Good. Any question on that? So it's not really anything new. We're using inverse tangent. We've done that. Pythagorean theorem, we've done that a lot. It's just how we're writing our answer. Right, so the reason why we're going to use trig form is it provides a quick way to multiply and divide. All right, let's take a look at how we would have to do division without trig form. Does anybody remember the name of what you multiply the top and bottom by? Good guess, not reciprocal. This begins with a C. Conjugate. Okay, whenever you want to divide complex numbers, you have to multiply top and bottom by the conjugate. Does anybody remember what the conjugate of 5 plus I is? 5 minus I. Good. Now, keep in mind, this one's not even that bad because you don't have a complex number in the top. You don't have a complex with a real and imaginary part. So to distribute, that one's very easy. Okay? If I had a complex number in the top here, I would have to FOIL. Okay, so it can be worse than what I'm showing you right now. Okay, but once we do this one time, this is all going to go away. I'm going to show you an easier way to do it. Okay, but for this type, now I would FOIL. 3 times 5 gives me 15. 3 times negative I, negative 3i. Now the bottom I have to FOIL up. Pat, what's 5 times 5?
25.
25. And now the next part, don't write yet, just watch what happens. 5 times negative I, 5 times positive I. It cancels out. Okay, so the middle part always cancels when you FOIL conjugates. What's a positive times a negative? Negative I times I squared.
Have you done this before?
Yes. Yep. So again, this is just a review.
Oh, I didn't even see that.
All right, so we got 15 minus 3i. But now we have to deal with I squared. Does anybody remember what number that is? Yep. Negative 1. Okay, so what I really have in the bottom is 25 minus 1. What's 25 minus 1? 26. And we're still not done. Now we have to separate it into real and imaginary part. So it's 15 over 26 minus 3 over 26 I. Right, so if we're going to divide complex numbers in what we call standard form, this is how you have to do it. Okay, and it's a pain. There's a lot of things you got to deal with. You have to remember to use conjugates. Then you have to distribute in the top. You have to FOIL in the bottom. Combine like terms. Change I squared to negative 1. And then separate the real and imaginary part. Okay, a lot of steps. And this one wasn't even as bad as it could be. Okay. So now I'm going to show you a much more efficient way to divide and multiply. Okay, you're going to be able to do it in your head. It's going to be very simple. All right, so this method relies on having your numbers in trig form. Okay, you cannot have them in standard form. So I've got 2 numbers in trig form. Okay, I'm going to call them z1 and z2. And I'm going to multiply them together. That's the first formula I'll show you. Each complex number has its own radius, which I've called r1 for the first number, r2 for the second. And each complex number has its own angle. Theta 1 for the first one, theta 2 for the second. When you do an actual problem, all of those will be numbers. All right, so we're not going to go through the proof of this formula because it's a little time consuming, but I think once I show you the formula for multiplication, you'll be able to tell me the one for division. You'll see a pattern. All right. So to multiply 2 complex numbers in polar or in trig form, take your radii, multiply them together. R1 times R2. Okay, that's the first half. Okay. The second half, take your first angle, take your second angle, add them up. That's it. Okay. So you multiply your radii and you add your angles. None of this distributing, foiling, I squareds, negative 1, none of that. Okay. Multiply the radii, add your angles. Yep.
Do you have to actually add the angles?
Yes, you add them. So if it was like a 10 and a 20, you would write 30. You would add them up. All right, so based on that, anyone think they can tell me what would I do with my radii if I'm going to divide? Z1 divide by Z2. So look at what I did with my radii here. think about what I would do here. Jamie?
You would divide radii 1 by radii 2.
Yep.
And then when you have the cosines of angle 1 and angle 2, you'd subtract instead.
Yeah.
And then you'd subtract the other 2.
So if you want to divide two complex numbers, remember how I just showed you we did it. That was where you found the conjugate, we FOILed, all that stuff. Okay? Now, all you have to do is divide the radii and subtract your angles. That's it. And of course, you can never divide by 0, so R2 cannot equal 0. Okay, does everybody have the two formulas for multiplying and dividing in trig form? All right, so let's look at an example. Okay, what I've done here is I've already changed them to trig form for you. Okay, in fact, -2 plus 2i. If you go back in the notes, I think that's one that we did. -2 plus 2i. Okay, we did it in degrees. Okay. I'm now doing it in radians. Okay, just to show you how I got 2.36. It was 135 degrees, but if you multiply by pi and divide by 180, watch what you get. 135 times pi, divide by 180. That's where the 2.36 came from. Just converted radians, degrees to radians. All right, so we've got both our points already in trig form. Okay, so that saves us some time. If they weren't in trig form, we'd have to do that first. Okay? Now, if you have to convert it to trig form, I'm not so sure how much time it's going to save you. If it's already in trig form, piece of cake. If not, whether you want to convert to trig form, it's up to you. All right, so let's find z1 times z2. Okay, what is my radius going to be when I multiply z1 times z2? Well, Brian?
10 square root of 2.
Yeah, 5 times 2 square root 2 is 10 square root 2. And when I'm multiplying, what do I do with my angles? Add them. So 0.93 is 2.36, and we're done. Okay, 3.29 radians. Okay. Any question on that? Mm-hmm. 10 square roots of 2, 5 times 2 gives me 10, and then square root of 2. It's kind of like if you had 5 times 2 with something attached. You just multiply what's in front and put after what was attached. So the root 2 was attached. All right. And let's look at z1 divided by z2. Okay, how am I going to find my radius for this one? What am I going to divide?
5 divided by 2 times 2 pi. I mean, 2 square root.
Yep, 5 over 2 root 2. So I'm going to do that down below because I wouldn't want to leave that as my answer. What's wrong with that?
Square root is fine.
Yeah, we don't want to leave the square root on the bottom, so we'll fix it. You just need to multiply by the root, not the 2, just the root 2. So that's going to give me 5 root 2 in the top. What's root 2 times root 2? 2 times another 2. 4. That's my radius. 5 root 2 over 4. Cosine. And what do I do to get my angles this time? Subtract. Okay. 0.93 minus 2.36. Now, something's going to happen here that didn't happen in the last problem. What kind of angle am I going to get? Negative. Okay, and generally we don't want to leave the answer as a negative angle. So I'm going to write it down for now. But we need to fix it. All right, there's a very quick way to fix it. And we mentioned this when we did sum and difference identities, okay, back towards the end of chapter 7. If you have the cosine of a negative angle, does anybody remember what you can do with the negative with cosine? You could just take it out. Okay, the negative with cosine doesn't even make a difference. You can just get rid of it. Now, the negative with sine, you can't just get rid of it, but where can you put it? You can put it on the outside. You can move it to the front. Okay, so that's how we can deal with a negative angle. All right, so we've got, that's one way. So 5 root 2 over 4. Cosine, what can I do with the negative on cosine? Just get rid of it. And what would happen if I move the negative to the front here? So we could say plus negative I sine 1.43, or even simpler, we could just change that to a minus. Okay, if you move the negative in front, it becomes minus I sine 1.43. Okay, those are equivalent answers. Okay, and the last way you can get rid of a negative on an angle is to add something to it. Does anybody remember in degrees where you can add to an angle to make it bigger? You can add 360. So what could you add in radians? 2 pi or 6.28. Okay, the disadvantage to doing it that way is you're going to make your angle a lot bigger. This way, you don't make your angle any bigger. You just get rid of a negative and move a negative to a different spot. But if you wanted to take the original and instead say, you know what, I'm going to get rid of this negative by adding 2 pi to it, that's fine. Okay, I added 6.28 and I got 4.85. These are both correct. You will not have to write both of these on the test. It would be one or the other. Okay, so these are different, but both are correct. Okay, one way you used an identity to get rid of the negative or move it. The other way you just added 6.28 to each number to make them bigger. Okay, any questions on that? All right, so arithmetic can get a little messy with the roots, but use the rules that you know, reduce roots, and just don't leave any roots in the denominator. Right. Do you guys want to try finding one of those on your own? We're not going to do both, but you want to try. Anybody want to try one of them? Think we got it? Okay. Well, what would you have to do with Z1 and Z2 first here before you could even use the shortcuts I showed you? You'd have to get them into trig form. Okay, so you'd have to find r and theta. I think we already have r and theta for one of these. We already did it. Okay. The other one is a new point. You would have to find r and theta. And then you could do what we did in this problem. Okay, but that would be step one. So step one, find trig form for Z1 and Z2. Step two, use the formulas. And you can deal with a negative any way you want. You can do it either way I showed you. Make sure you're comfortable with both in case on the test it asks you to do it one way. But as far as the homework, whatever way you want. Does everyone have what's on the left? All right, so the homework tonight is on 450. Okay. Some of it's just graphing, so they're pretty quick. Some of it is doing what we just did in the last couple problems. So it's 1 through 3, 5, 8, 11 through 14, 17 through 20, 33, 34, and 37. Okay, we'll take a look at that tomorrow, and we'll finish up trig form of complex numbers tomorrow.